Hi kids, welcome to a new weekly science lab video. In former videos I mentioned gravity and I referred to it as a force because it makes objects accelerate towards each other. The truth is that about a century ago, another great influencer of science came to contradict Sir Isaac Newton himself in this sense. This would be none other than the German physicist Albert Einstein. The physics proposed by Einstein is like a 2.0 update of the one proposed by Newton 400 years earlier, which turned out to be obsolete when it came to studying the behavior of light and how it spreads through space. In particular, the fact that speed of light is always the same, roughly 300,000 kilometers per second, and that despite having no mass at all, it is attracted to supermassive objects such as black holes deflecting its trajectory, forced Einstein to rethink everything established by Newton about motion. Do not consider this as a failure or a mistake on Newton's part. Nothing could be more untrue. This is exactly how science is built. In the words of Newton himself,
"If I have seen further, it is by standing upon the shoulders of giants."
In this case, Einstein's upon Newton's shoulders to see beyond through a new knowledge obtained thanks to technological advances. However, Einstein's physics is way too complex to apply on day-to-day basis. So, for everyday mundane matters, we will continue to use Newton's laws. Hence, let's keep on treating gravity as a force. Gravity, therefore, is the result of the interaction between two bodies with mass by means of which each body applies on the other a force of attraction. Newton discovered the following.
There is a power of gravity tending to all bodies, such that the weight of either body towards the other will be proportional to the quantities of matter which they severally contain, and reciprocally as the square of the distance between their centers.
That is to say that these forces of attraction between two bodies are equally intense, which means that both bodies attract each other equally strongly, and in addition, that the bigger the result of multiplying the masses of the two bodies, the stronger the intensity is, and the smaller the distance between the two bodies, the more intense it is. Wait a minute, did you just say that any two bodies would attract each other equally strongly? Does it mean that not only the Earth is attracting my body, but also my body is attracting the Earth? Then why am I unable to see that the planet is moving towards me, but quite the reverse? It does, but in a proportion that is inverse to how bigger the Earth is in relation to the size of your body. And really, any two objects in the universe? So not only the Earth and me, but also this mug and Jupiter? Are you seriously saying that this mug is attracting Jupiter as strongly as Jupiter is attracting it? So why is it not moving towards Jupiter then? It's just because the mug is under a much stronger gravitational force, which is Earth's. It's true that Jupiter is much more massive than the Earth, in fact 3018 times. But at its closest point to us, it is 588 million kilometers far from us, which makes the attraction much weaker, but not non-existent. The force with which an object is gravitationally attracted to another is what we call weight. Therefore, my weight on the planet Earth will not be the same as on the Moon, for example, since, although my mass is the same, the mass of the Moon and the Earth are very different. So, because the Moon is much smaller than the Earth, and therefore has less mass, my weight on the Moon is less. This is the cause of the feeling of weightlessness that we so often associate with astronauts. So we have just understood something very important. Weight and mass are not the same thing, although they are related. This is a fascinating and exciting subject, no doubt. Do you want to put into practice some of what you have learned about gravity and weight? Well, let's do it. Roll up your sleeves, for it is experiment time. We are going to need a weighing scale, If you don't have one at home, check the other video I am attaching to this task, in which it is explained how to make our own homemade weighing scale with a hanger, an object to weigh, and a piece of string. Just weigh the objects. If you are using a conventional scale, it will display a measurement in grams or kilograms, but you know those are units of mass. And you are right, don't be fooled. The point is that as we used to live on the planet Earth by now yet, our terrestrial weighing scales are prepared to display the result of the measurement directly converted into mass. But if we use them on the moon or anywhere else in the universe, they would be useless. Let's prove it. Note down the measurement of the mass of the object and weigh it again. But this time, tie a piece of string around the object. Before removing the object from the scale, pull the string a little bit and observe how the measurement of mass changes. But is the mass of the object actually changing? No, the object has the same mass all the time. It is the weight what changes, because we are counteracting the force of attraction between the object and the earth by pulling the string. If you are using your do-it-yourself weighing scale, then there are not going to be numbers displayed, but you are going to be able to measure the weight at a rough guess. The important thing is to be able to perceive the variation in weight when pulling the string. What do we learn then? Exactly. Mass and weight are different things. Mass is a property of the object itself, and it doesn't change unless the object itself changes, while weight is a measurement of the intensity of the gravitational force exerted upon it, and it changes depending on what is the body that exerts that gravitational force. That's why an astronaut's mass is the same, regardless of where he or she is, but his or her weight is quite different on the Earth than on the Moon, for example. I hope you enjoyed this activity. See you!